Let's do section 10.5, page 528, exercise 23, which reads, determine whether the series converges absolutely, converges conditionally, or diverges. Give reasons for your answer. Find a bound for the truncation error after 99 terms. So our series for exercise 23 is the summation from n equals 1 to infinity of -1 to the n plus 1 times 1 plus n over n squared. Now the first thing you want to notice is that that factor right there tells us that this is an alternating series, and that means that we're going to be able to apply certain theorems, certain rules to the situation. So the first thing that we need to do is test for absolute convergence, and we need to use what we learned in section 10.4. So I'm going to start by taking the absolute value of my series. So that's going to be -1 to the n plus 1 times 1 plus n over n squared. And when I take that absolute value, I'm going to get rid of that -1 term, and this is going to give me the summation from n equals 1 to infinity of 1 plus n over n squared. And I'm even going to write this a little differently. I'm going to have 1 to infinity of 1 over n squared plus 1 over n. And now we could actually use the direct comparison test because we know that the series from n equals 1 to infinity of 1 over n diverges. That is a p-series with n equals 1, and we know that that's a p-series with p equals 1, and we know that in that situation, the series is going to diverge. So I know that 1 over n plus 1 over n squared is going to be bigger than 1 over n. So if 1 over n diverges, and all of these terms are going to be bigger than the terms in a series that diverges, then that tells me that this series is going to diverge as well. So the answer is we do not have absolute convergence. So the next question we have to ask ourselves is, do we have conditional convergence? And because this is an alternating series, we can use theorem 12. And just to remind you, theorem 12 says an alternating series converges if all three of these conditions are met, if each term in the series, discarding the plus or minus sign, is positive, if the terms are getting smaller after a certain point. And finally, if we take the limit as n goes to infinity of un, if that is equal to 0. But remember that all three conditions must be met. So for our series, we're going to have un is going to be equal to 1 plus n over n squared. And for n greater than or equal to 1, all of our uns are going to be positive. So we satisfy the first criteria. So our second question is, are the uns greater than or equal to the un plus 1s? Well, this is saying that we are going to have 1 plus n over n squared, and we're asking ourselves, is that going to be greater than or equal to 1 plus n over n plus 1 squared? And I'm not really sure that it is immediately obvious if that's true. So is there a better way that we can ask about condition 2? Well, we could probably use some other calculus that we know. So for instance, if I let this be a function of x, and I had 1 over x squared plus 1 over x, which is really what my function is up here. If I took the derivative of that, then I'm going to get -2 over x cubed minus 1 over x squared. And that's going to be less than 0 for all x greater than 0. And in this case, x is really n, and I've already said that n is going to have to be greater than or equal to 1. And this tells me, because my derivative or my change is less than 0, this tells me that the terms are getting smaller. So our second criteria is met. And finally, our last condition here is to say that the limit as n goes to infinity of un, which is going to be 1 over n squared plus 1 over n, has to be equal to 0. And in fact, just by looking at that, we're going to end up with 1 over infinity plus 1 over infinity, and that will be equal to 0. And that tells us that this is conditionally converging. All right, well, the last thing we have to do is calculate the truncation error. And for that, we can use theorem 13, which is only for alternating series. But it tells us that the error for the 99th term has to be less than whatever the value is for the 100th term, and that this truncation error is going to have the same sign as that first term we don't use, which is going to be, again, negative 1 to the 100, which is going to be equal to 1. So our truncation error will be positive. So we can say that a bound for the truncation error is going to be u of 100, which is going to be 1 plus 100 over 100 squared, which is going to give us 0.0101. And it will be positive, and that's our answer.